Hello, I'm Hugh Ross, and welcome to Stars, Cells, and God. Today we'll be exploring some of the exciting concepts and topics in my new book, Designed to the Core. Designed to the Core is a culmination of decades worth of research and breakthroughs in science. I couldn't be more enthusiastic about the work we completed. My latest book is set to release widely in September 2022. However, today I'm privileged to share with you that are partners of our Reasons to Believe ministry. You'll be able to receive early access to this resource before that launch date. To receive early access to this book, all you have to do is visit reasons.org/donate and make a donation of any amount to our ministry. Then in early August, or perhaps earlier as soon as we get the books, you'll receive a copy of my newest book, Designed to the Core. Now, for those of you who are already supporting our ministry regularly, you can expect to receive the book in early August as well. I could not be more pleased to share this resource with you, and I hope it inspires you to share the book with others. For more information, please visit reasons.org/donate. Now for our topics for today, and Fuz, you got an amazing discovery to share, but I'm going to launch off with something that has to do with black holes. And so this actually is an image of the first black hole that was ever been in. This was done in 2019. And it was done by what's called the Event Horizon Telescope, an amazing instrument. What they did, astronomers took the largest radio telescopes, arrays of telescopes and radio telescopes from all over the world, and linked them together through computers and TV technology and atomic clocks. And we're able to produce a telescope that has the equivalent resolving power of a 6,000 mile diameter telescope. So it has 4,000 times the resolving power of the James Webb Space Telescope. It's the only telescope that is sensitive enough in terms of its resolving power to actually image the event horizon of a black hole. Now, for people not familiar with black hole physics, the event horizon is the distance from the black hole where the gravity of the black hole is so powerful nothing can escape, not even light. And so anything inside the event horizon is going to look completely black. But outside the event horizon, you're going to have really bright light. Why? Because as matter is being drawn in by the gravity of the black hole towards the event horizon, matter is being converted into energy with anything from 10 to 42% efficiency. So these are the brightest objects in the universe. I mean, to give you a comparison, the nuclear furnace inside our star, the sun, converts matter into energy with 0.07% efficiency. So we're looking at hundreds of times more efficient conversion of matter into energy, which explains why astronomers anticipated that when they actually had this kind of telescope with that resolving power, they would see these black holes that look like a donut, where you got bright light outside the event horizon and nothing but black inside the event horizon. And what you see here is the very first image taken of the event horizon of a black hole. And this is the black hole that's inside the galaxy M87. That's a supergiant galaxy inside the Virgo cluster of galaxies. It's 53 million light years away. And you say, that's awfully far to be able to see a black hole. The reason why astronomers chose this object is that it's a supermassive black hole, weighs in at 6.5 billion times the mass of our star, the sun. Also, by being a supergiant spheroidal galaxy, which means the matter is very densely concentrated around the center of the galaxy, which means there'd be copious amounts of matter being sucked in towards that black hole, which explains why you get this bright donut around it. So this is actually the easiest black hole to image. So that's why they chose that one first. But the real goal was to image the event horizon of the supermassive black hole at the center of our galaxy. But it took 4 years of dedicated observations by this array of radio telescopes around the world to get sufficient sensitivity that they could actually see the event horizon. And that's because and our Milky Way galaxy, its supermassive black hole, comes in at only 4 million times the mass of our star, the sun. Sounds like a lot, but that's incredibly tiny for galaxies of the size of our Milky Way. I mean, the sister galaxy, the Andromeda galaxy, has the same mass as our Milky Way galaxy, and it's a spiral galaxy just like our galaxy is. Its supermassive black hole comes in at 140 million times the mass of our star, the sun. So the Milky Way has a supermassive black hole 35 times smaller. Nevertheless, astronomers felt, hey, it's close by. It's only 26,500 light years away. We should be able to easily get an image. It turned out to be extraordinarily more difficult. But just a couple of weeks ago, they did release what they called a preliminary image of the event horizon of the Superman. This is what it looks like. And it's a preliminary image because you notice that the event horizon, that little black spot, barely noticeable here. I mean, it's not like the one that you see with M87 where you get a clear black region inside the event horizon, quite well defined. Notice this is not well defined at all.
Right.
And but over the 4 years, they were basically focusing on that bright donut around the black hole. And what they noticed was that it did vary, but the degree of variation was at the 5% level. So, and they were anticipating they would see a lot more because what creates that big bright donut of light is matter being sucked in towards the event horizon. And the anticipation was, well, we're going to see relatively big objects being sucked in which case when they actually go into the event horizon, you're going to get a huge burst of light. They weren't seeing these bright bursts of light. They were seeing variations, but they were subtle. And moreover, what they recognized is they weren't getting the radiation around the black hole that they expected, which is why it had to take them 4 years to accumulate data, even to get this, quote, preliminary image. But they wound up publishing 10 papers, a special issue of Astrophysical Journal Letters. And a typical issue will have maybe 15 papers in it. 10 of the papers were devoted towards the discoveries by the Event Horizon Telescope team. And so I've written a blog on this that's going to be part of my Today's New Reason to Believe, where I cite material from paper 3 and paper 5. But what's fun is the Astrophysical Journal Letters have decided to make all 10 papers public access, which means you don't have to pay any money. You can read the entirety of all the papers for free. So if you go to the Astrophysical Journal Letters website, you can look at those papers, and they're quite readable. You don't have to be a PhD level astrophysicist to be able to understand what they're talking about. But I will give you the bottom line. So yeah, they published 10 open access papers. It's in the May 10th issue of the Astrophysical Journal Letters, so people can go there. But they found out that the Milky Way's supermassive black hole is consuming the mass equivalent of about 1/5 the mass of our moon per year. This is way lower than what they expected. So they basically said, wow, it's not really pulling in much matter at all. Even over the entire year, it only adds up to 1/5 the mass of the moon. But they also noted that the light variations in the donut outside the event horizon, they occur in time scales between about 1 minute and 1 hour. But the average was about 10 minutes, which means it's pulling in tiny amounts of matter on a rather regular basis. Rather than getting a big chunk of matter coming in, say, once a month, what they're getting are tiny amounts of matter coming in on the order of minutes. So again, this is an unusual feature. when you look at the one on M87, you see these big flares coming out, and we're not seeing that with ours. And then they also noted that the light variations, as I've already mentioned, is at about the 5% level, which means that it's probably pulling in gas and dust at a rather regular level, and occasionally it brings in something a little more like a meteorite. And that would explain the 5% variation. But when you add up the total amount of mass we're talking about here, the supermassive black hole consumes the equivalent of a comet or asteroid about the mass of Phobos about once every 10 minutes. So every 10 minutes is consuming the equivalent of the mass of Phobos. That's one of the tiny moons orbiting Mars. And but with 5% variation, it doesn't mean it's pulling in an asteroid the size of Phobos every 10 minutes. It means it's pulling in the mass equivalent of Phobos every 10 minutes. And so this is what Phobos looks like. And it's about 22.5 kilometers across, or 14 miles across. So this would be in the category of a relatively small asteroid that's being pulled in on average every 10 minutes. But really what you're getting is gas and dust that adds up to the equivalent of Phobos. And occasionally you get something a little bit bigger. And then the astronomers actually measure what they call the bolometric luminosity. Now that's a technical term which means the luminosity of that supermassive black hole across the entirety of the electromagnetic spectrum. So from long radio all the way to gamma rays. That's the total. We're not just talking visible light. This is the total luminosity. And it came in at 8 times 10 to the 35 ergs per second. But what I did here was, and this wasn't in the paper, but I compared it with the sun's total luminosity. And bottom line is the luminosity of that donut around the supermassive black hole, the center of our galaxy, it comes in about 200 times what our sun is, which again is extraordinarily low. For something 4 million times the mass of our star, the sun, to be shining with a light of only 200 times what we're getting of the sun means it's exceptionally low. Bottom line, this is a confirmation for what I wrote in the Design to the Core, that in the last million years, what we've seen is that the supermassive black hole in the center of our galaxy has gone into an extraordinary phase where it's pulling in very little matter, and the matter it is pulling in is rather continual, tiny amounts, predominantly gas and dust, with occasional larger materials. And we literally see flares coming out of there every minute or two, or every 10 minutes or 20 minutes. But the flares are such a tiny level, it poses no risk to advanced civilization here on Earth. But we know it wasn't always like that because of what we see in this image here. These are X-ray, gamma ray bubbles, and astronomers have been able to detect chimneys of X-ray radiation that connect these bubbles right to the supermassive black hole, which means just a couple of million years ago, there was a major episode which generated these bubbles. And what you're seeing here is the norm for a supermassive black hole. If it pulls in an asteroid or a body as large as the moon, say it pulled in a body as large as the moon, as it comes into that towards the event horizon, 30% of that would be converted into pure energy, which would create a huge burst of deadly gamma and X-ray radiation. And what we see here, what they did is they measured the velocity, the expansion of these bubbles, which was able to tell them, hey, about 2 million years ago, there was a major event where it may have pulled in a body as big as a planet. Bottom line is that's the norm for supermassive black holes, that it's going to be, because at the center of a galaxy, there's a very dense, that's the densest part of our galaxy. You've got literally trillions of, or billions of, hundreds of billions of stars there. And so you've got all kinds of planets, comets, asteroids, stars. So the anticipation is the black hole is going to be sucking in some big objects. And when it does, you get flaring events that would be deadly for humans and human civilization. But right now, we're in a narrow window of time where our supermassive black hole is in an incredibly quiet phase, where it's not pulling in anything big. All it is pulling in a small amount of gas and dust, which means it's possible for us to safely launch and sustain a global high-tech civilization. And something else I put in Design to the Core is that when you look at the Andromeda Galaxy, its supermassive black hole is 35 times bigger. But just like the supermassive black hole in our Milky Way Galaxy, right now, its supermassive black hole is in a quiet phase. And so the Andromeda Galaxy's supermassive black hole doesn't threaten advanced civilization on the Earth, neither does the one. And kind of what I'm suggesting in Design to the Core, somebody beyond the universe is fixing everything so that there is no danger. I mean, Neil deGrasse Tyson, not a theist, but he has made the point the universe is out to kill us.
Right.
And everywhere you look, you see these hostile conditions. But we're seeing with the Andromeda Galaxy and our galaxy, the supermassive black holes in both cases are in a quiet episode where it's not going to kill us. So, and if people want to read more, it's in Design to the Core. I also put this in a peer-reviewed paper that got published, and people can access that by going to Black Holes as Evidence of God's Care. So they can take a look at that to get an advanced look. But all these figures are going to be in the new book, Design to the Core.
Yeah, pretty remarkable that that you see this quiet period for the black hole at the center of the Milky Way Galaxy, that again corresponds to other design characteristics like the solar flaring.
Yeah, remember last week we talked about the sun being in an exceptionally quiet phase in its history, and all these quiet windows are simultaneously lining up.
Yeah.
So, yeah, thanks, Fuz.
Yeah.
Okay, I want to hear about your discovery.
Okay, sure thing. And I'm just going to take a second. And Hugh, I don't know if you think about your time in graduate school a whole lot.
I have nightmares, Fuz.
Yeah. Well, I have my share of nightmares too when I think about my time in graduate school. But it also, on the other hand, was probably one of the best periods of time in my life too. There was a lot of fun being in graduate school.
It was a lot of fun, but I'm sure glad I was young when I was in graduate school.
Yes, yeah. It was a lot of work. It was hard work, to be certain. And there were times where I was wondering, why am I putting myself through this? But and also part of the graduate school experience is not only learning how to do science and learning the information you need to be an expert in a particular area of science, but there was also this process by which your professors from time to time felt like they needed to remind you of your pecking order in the academic hierarchy, right? And one of those instances happened shortly after I joined the research group that I was part of in graduate school. And my PhD advisor gave me my first lab assignment, which was to clean the lab.
To clean the lab, okay.
Yeah. And it wasn't just washing the dishes on the lab bench and organizing the lab bench. He wanted me to go through every drawer in the lab and clean it out and organize it. Well, one of the drawers that I went through was the drawer that held the accessories for our ultra centrifuge. We had this ultra micro centrifuge. And as I was going through the drawer, there was, of course, rotors and little tiny micro centrifuge test tubes and things like that, wrenches. And there were these straws that were in the drawer that were cut into pieces. And I'm sitting there thinking, okay, who on earth would put straws in this drawer, right? To me, it just looked like junk that somebody had jammed into the lab drawer.
These were glass straws?
No, they were plastic straws.
Plastic straws?
Yeah.
Oh, that would be even weirder.
Yeah, so I just figured this is trash, so I threw them away. Well, that was a bad move because it turns out that those straws were actually part of these accessories for the microcentrifuge. They were actually part of the pipette system that was used to move samples in and out of the microcentrifuge tubes. But just for fun, I actually went online to see if I could find the microcentrifuge that I used in graduate school. And this is one of the rotors. And so these little rotors actually, it was an air compressor that ran the microcentrifuge. So it sat on a bed of air and then could rotate at, 100,000 plus RPMs.
Oh, wow.
Yeah. So, and these test tubes were really very tiny. They're about that big. Mm-hmm. And so we would use it to concentrate basically cell membranes that we would purify from bacteria so that we could transfer them onto a infrared plate so that we could record the infrared spectra. But anyway, there was a lesson that was, that's to be learned from that, and that oftentimes we see things that we think are junk, and it turns out to have a perfectly good explanation for why it's there, what its function is. Because I don't think anybody would dispute that straws are functional. They're useful to help you drink, And if you saw a straw in the restaurant, you would immediately, it's where it's supposed to be. It wouldn't be, you wouldn't be surprised to see it there, but you wouldn't expect to see a straw, let alone a straw that was cut up into pieces in a chemistry lab drawer.
Well, moreover, we wouldn't expect a pipetting device to be just a plastic thing.
Yes.
So.
Yeah. Well, it turns out that this lesson applies to what life scientists are learning about genomes. And that is that there are elements, sequence elements in genomes that seem to be, that everybody just assumes are non-functional. And it turns out that the more we learn about these systems, like the more I learned about how the microcentrifuge worked, the more that, the more that we are recognizing that these are actually, in the genomes for a reason. And one of those classes of sequence elements are called endogenous retroviruses. And many people see endogenous retroviruses in genomes as being, again, out of place, that these are sequences that resemble the sequences of a retrovirus. And so if you see a retrovirus sequence, in a viral capsid, you immediately understand it to be functional. But if that sequence is in genomes of an organism, it's not supposed to be there. So it must not be functional.
Yeah, and this is a key argument for naturalistic evolution, the fact that we see these, quote, mistakes,
right.
Pieces of the genome that shouldn't be there. And hey, if it's a mistake that we see in another species, that kind of
right.
used as an argument for common descent.
Yes, and I'm glad you brought that up because that's exactly the point I was going to make.
Oh, I'm sorry.
No, it's good. It's good because for many people, particularly with endogenous retroviral sequences that are shared in the human genome and the genomes of great apes, they argue that this is unassailable evidence for common descent.
Right.
And just to give a little bit of background as to why many people see this as being such a compelling argument for common descent, this is a cartoon showing the sequence elements of the genetic material for a retrovirus. A retrovirus's genetic material is made up of RNA, not DNA. And what's shown here is that this is again a schematic of the RNA sequence, where different regions of the sequence are labeled according to the information that they harbor. And so the two ends of the RNA sequence that are labeled 5' and 3' consist of what are called LTR sequences, or long terminal repeats. Mm-hmm. And it turns out that these sequences actually have what are called promoter sequences, which are sequences where enzymes like RNA polymerase will bind to. And then you have these three other regions that encode protein products that, like the GAG and the ENV, encode protein products that are used to assemble the viral capsid. And then the PAL sequence codes for proteins that are involved in the life cycle of the retrovirus. And so this is another cartoon showing how a retrovirus operates. So if you go to the left-hand corner, that's a schematic of the retrovirus that binds to the cell surface and then introduces its genetic material into the cell, which would be the the viral RNA. And then some of that viral RNA is actually translated at ribosomes, and as part of that process, it produces a number of enzymes. One of them is called reverse transcriptase, which will convert the viral RNA into a piece of DNA. There's another enzyme called an integrase that will integrate it into the genome of the host cell. In that genome, then it can be transcribed into viral RNA that then, along with the protein products that form the capsid, can be encapsulated and released from the cell to infect other cells. Sometimes that viral RNA will get, again, an integrase will take that and introduce it into another region of the genome, so you can get essentially a multiplication of that sequence in the genome. And this is a process called retrotransposition.
Right.
Now, this is essentially called the horizontal infection cycle, where the virus that's released is going off to infect another cell.
Right.
If the cell, according to, again, the evolutionary framework, if that cell that is infected with the retrovirus is a germ cell that's going to become a sperm cell or an egg cell, then that retroviral sequence will be transmitted to the next generation. That's called a vertical infection or a vertical transmission. And this is the basis for why people claim that this is such powerful evidence, for human evolution. Because the idea here is that if these viral sequences are essentially transmitted to subsequent generations, then they become a tool that can be used to monitor essentially the history of that genome. And the fact that you see, again, these shared endogenous retroviral sequences among the great apes and humans suggests to people that this is evidence for our common ancestry, that this is evidence for human evolution. So it's actually a very compelling argument. I would agree with that. But yet there are a number of reasons why I'm skeptical that evolutionary mechanisms can fully account for the history of life on Earth. And I'm not going to get into those here. But if you adopt that perspective, which is why I'm an old Earth creationist, not a theistic evolutionist, if you adopt that perspective, then you actually have the responsibility of explaining why a creator would intentionally introduce into genomes of organisms these sequences that look like retroviral sequences, right? That are shared among organisms, where the corresponding sequences occur in corresponding regions in the genomes of different organisms, and you have to demonstrate functionality. So there's three criteria. Are these sequences functional? Why do they look like retroviral sequences? And why are they distributed in the way that they are?
So from an old Earth creationist perspective, God doesn't make junk.
Yes.
And so, then it's the onus is on us to show, that this is not junk.
And we have to go one step beyond just simply saying it's functional. We've got to explain why it looks the way it looks.
And why we see it in these different species.
Exactly.
Why we see the sharing.
Exactly. And so this is a paper that was published just recently in a journal called the Journal of Virology by a team of Japanese researchers who actually give some very important understanding as to what endogenous retroviruses are doing. And it turns out that we've discovered in the last 4 or 5 years a number of different functions that endogenous retroviruses perform. And those functions actually relate to the fact that they have sequence similarity to retroviruses. But one of the functions that they serve is to actually protect early stage embryos from retroviral infections. When an embryo is in the 2, 4, 8, 16 cell stage, it's extremely vulnerable at that point and could easily be infected with retroviruses. And it turns out that people have discovered that at the very early stages of embryonic development, there are endogenous retroviral sequences in the genomes of, again, these early embryo cells that are expressed at high levels. And this is providing essentially a protection mechanism from retroviral infections. Also, some of the there's a particular retroviral protein called the REC protein that can actually interact with ribosomes and influence the rate of translation of RNA transcripts. And this is also active as well in the early stages of embryonic development. And that seems to also regulate gene expression patterns that are playing a role in the development and the differentiation of early stage embryos. So these endogenous retroviral sequences are playing an antiretroviral role. And this is a cartoon that kind of helps see how that happens, because when the endogenous retroviral sequence is expressed, okay, first of all, you're going to have RNA molecules that are accumulating in the cytoplasm of the cell that are endogenous retroviral RNAs. Some of them will be translated into these protein products that are analogs to the capsid proteins that are used to assemble the retrovirus. So if a retrovirus happens to infect the cell, these endogenous retroviral RNAs in the GAG and the ENV proteins essentially competitively inhibit the assembly of the retrovirus.
I see, yeah.
So it essentially disrupts the life cycle of the retrovirus, which is why the ERVs have to look like retroviral RNAs, and
Right.
and then you can now see that the shared sequences are actually reflecting common design, not common descent. Okay, so
Because we're not going to be the only species facing this challenge.
yeah, exactly. Now, it turns out that once the embryo matures beyond the early embryonic stages, the expression of the endogenous retroviral genes are shut down.
So how soon after?
I'm not exactly sure at what point that happens, but it's at the point where the embryo is beginning to differentiate
Okay.
into going from the kind of the blastula stage to a gastrula stage. So it's very early on in the process it's shut down. And in fact, throughout most of our lives as adults, the endogenous retroviral sequences in our cells is suppressed. The expression is suppressed.
Well, like for us humans, this suppression would take place, what, roughly 1 week after conception?
Thereabouts,
Yeah,
in that
okay.
neighborhood, yes. And there's actually a methylation of those sequences. So it's an epigenetic regulation that essentially shuts down the expression. If these sequences become unregulated and they start to become expressed, that's not a good thing. It actually leads to cancer and to other kinds of genetic diseases, because now you have these endogenous retroviruses undergoing retrotransposition, where they're making copies of themselves and inserting randomly into different regions of the genome. That's not a good thing.
Right, yeah.
Right? And so, well, it turns out that this is where the work of the Japanese scientists comes into play. What they discovered is that there is a particular transcription factor called SOX2 that is involved in essentially the very early stages of embryonic development. When the SOX2 protein is expressed, it keeps the embryonic cells essentially in a state of pluripotency. It keeps them from differentiating. As soon as that expression of the SOX2 protein stops, the differentiation process happens. So that's kind of illustrated here.
Mm-hmm.
And there's other transcription factors, OCT4 and NANOG, that are also involved in maintaining pluripotency. And they're shut down early enough so that in the embryonic development process that, again, this differentiation happens. Well, it turns out that SOX2 regulates the expression of endogenous retroviruses. It actually binds to the promoter in the long terminal repeat region, and when it binds, it causes the expression of the endogenous retrovirus. When you remove SOX2, that expression is shut down. And so what is being revealed here is not only, again, this idea that, again, the endogenous retroviruses have function, and their function is intimately connected to their sequence similarity to retroviruses, but what it's also showing is that this is precisely regulated during the course of embryonic development, so that these sequences are expressed when they're needed and then shut down when their expression would become deleterious.
Right.
So this is just showing what it's creating is this really elegantly designed package of design elements, right? That from an old Earth creationist perspective explain again why these endogenous retroviral sequences are in genomes, what role they're playing. But the fact that there's this precise regulation suggests design to me. So this is not just a haphazard system.
Yeah, the timing's perfect.
Where these sequences just happen to acquire functionality. It's tightly regulated, which means that if it's not tightly regulated, it's going to wind up being catastrophic for the developing embryo. And so that precise regulation makes it very difficult to envision how something like this would have emerged through some kind of stepwise evolutionary process. It's a type of system you'd expect to see if it was intentionally designed to be that way. Now, this doesn't necessarily mean that an evolutionary interpretation of endogenous retroviruses is undermined, but what it does mean is that if you hold to an old Earth creationist perspective or a design perspective, that there's an elegant explanation for why a creator would introduce these sequence elements. And so that means that these are no longer a liability to an old Earth creationist position, these particular sequence elements, but rather it becomes part of the case for design that we would mount.
It'd be a stronger case if you can demonstrate that this is design we see not only in the human species, but many other animal species.
Well, and precisely that's the case, is that we see that across the board,
Wherever it's needed, it's there, and where it's not needed, it's missing. Is that correct?
Yes, right.
Fantastic.
Yeah, and so, it's interesting because I remember when I started at Reasons to Believe many years ago, it was very difficult to really respond to the junk DNA challenge. I mean, there were a few things we could have said, but it wasn't anything, really comprehensive.
I remember back in those days, Fuz, we would use the analogy, well, we used to think that some of the organs in the human body were junk, and they turned out not to be. And so I remember you making the prediction, I think this is going to happen at the biochemical level.
Yeah, and so we made a prediction, and there's a blog article that I wrote in 2000 where I made that prediction.
I just read that a few days ago.
But there was really nothing that would suggest that prediction, at least at that point in time, had any real chance of being fulfilled. It was a conviction that we had based on our view that the genomes must be designed. And lo and behold, here we are, a couple of decades later, and there's just been an avalanche of discoveries demonstrating design for not only endogenous retroviruses, but all kinds of different sequence elements that have been labeled junk DNA. And so it really is highlighting the fact that we are in our infancy in our understanding of the human genome, and that we want to be probably circumspect about declaring sequence elements to be non-functional, to be useless, until we actually learn more, because the trend line is the more we learn, again, the more that we see functionality. And it's unexpected functionality in many instances.
Well, Fuz, a hallmark of Reasons to Believe is our testable creation model, where we're making the point that, hey, future scientific discoveries are going to fulfill the predictions we make. That article you wrote in 2000, highly readable. You really explain all the basics for lay people. It's up on our website. People can read it for free. If you just put, endogenous, I think all you have to do is put retroviruses.
Well, actually, I think it was just junk DNA, not so junky or something, maybe.
Yeah, some kind of title like that. But I just put into the search engine retroviruses. It popped right up. I think even if you put viruses in, it pops up. Okay. So it's easy to find. But the article was written in 2000. And what I love about that is how easily and simply you explained it all, but you made some bold predictions that today clearly have come true.
Yeah. And again, it's not that I'm prophetic or anything like that. It really were predictions that were made out of a conviction that the human genome is actually designed.
Right.
And so anyway, but that's all I've got. So
yeah, well, again, I just encourage everybody who's watching, do go to reasons.org. Look up that article that Fuz wrote in 2000, and then compare it with the articles he's writing in 2021 and 2022. To me, it's a mind blower just comparing those articles. So encourage people to do that. Well, once again, I want to encourage people that, go to RTB_official, and that will be your gateway to all kinds of online resources you can get at Reasons to Believe. And yes, I want to remind you again about the offer we're making for my next book, Designed to the Core. If you go to reasons.org/donate, you'll be able to get in advance of the general release a copy. For a donation of any amount, we'll send you a copy of Designed to the Core, and you'll be getting it about 6 weeks previous to the general release. So you'll see all the details on our website. And I thank you for watching this. And again, this is all archived on YouTube, so you can tell your friends about this, and they can watch it at their leisure. Thank you.